topics that we're going to be going through. What's chemistry? What are observations and how do we make them? Different units of measurement. What are the temperature scales and how can I convert between them? What's scientific notation and how do I use it in measurements? And what are significant figures and how do they affect my rounding off calculations? So the first thing is, what is chemistry? Well, chemistry is the study of matter and the changes it undergoes. We see the changes around us all the time. When milk goes bad, we note the changes. When you make some toast, you see the change in the bread. Now, matter itself is anything that has mass and occupies space. Occupying space means it has volume. Now, how do we study matter? We study matter by observing it. When you observe it, you ask yourself some of these questions. Is it a solid, liquid, or a gas? Does it have a color, a shape, an odor? What does it look like? Anything you recognize? Is it warm or cold? Is it heavy or light? We can put observations into two different categories. One is qualitative, which denotes some quality of the substance like color, shape, or phase. And the other type is quantitative, a measurement or comparison. So when you think of quantitative, you talk about using a balance or a ruler or something like maybe a graduated cylinder, something to measure a property of a substance. Here are some of the units that we use in the metric system. And SI stands for the International System, which is pretty similar. You'll see some changes like in volume and mass. In this country, we use a combination of it, so we kind of use a pseudo-metric system. This here is just showing you the difference between yards and meter sticks. A meter is about 3 inches longer than a yard being 36 inches. For volume, we have a liter and a quart being very close. You notice that a quart is actually a little bit less than a liter, 946 milliliters. And here we are weighing a chocolate, and we're weighing it in grams because that's the basic unit of mass. And we're getting 3 digits to the right of the decimal point. So that's a pretty good amount. So we have 23.089 grams. So we measured it all the way to the thousandths place. Now on to temperature scales. We have centigrade and Kelvin here. You might have a thermometer like this outside your home. I have one outside a window so I can see what it is, especially in the winter. So let's see. You can notice that here we have, it looks about 66 or so maybe Fahrenheit, and that's around 19 maybe, 18, 19 degrees centigrade. I'm trying to read that. So you notice we're not too accurate with this. It looks like the Fahrenheit scale has more graduations versus the centigrade, so it might be a little bit more accurate. We have a couple of formulas for calculating temperature changes. One is for Fahrenheit and centigrade, and the other is for Kelvin and centigrade. And many of you may not have heard of the Kelvin scale before, but the Kelvin scale is based on the motion of molecules. The faster molecules move, the higher the Kelvin temperature. The slower they move, the lower the Kelvin temperature. When molecules are no longer moving at all, they're at 0 degrees Kelvin, and that's called absolute zero. The other two temperature scales are both based on the boiling point and the freezing point of water. Now here are 3 questions that you can try before going any further to see if you can get them right. So you might want to stop the video and write these down on paper and come up with the answer, and then come back and see the solutions done out. Okay, on to the solutions. Now here's the first one. I write down my formula. I make my substitution. For the centigrade, I put in a 30. I do the math, and there is that. So 86 degrees Fahrenheit is my answer. Couldn't be simpler. But I'm going to use the same formula for the next one. Here's my question. Now, here's my formula, same formula. Now this is what I'm doing different. I'm going to make my replacement. So 30 goes in for the Fahrenheit. I'm going to put an X in for the centigrade symbol. Now I want to get X by itself, so I'm going to subtract 32 from both sides. That'll give me minus 2 equals 1.8x. And then I'm going to divide both sides by 1.8. So I'm going to draw my line here. So here's my line like that. Here's my line. Now these would cancel out, and then I would solve it, and I'd get minus 1.11 degrees centigrade is equal to X. Pretty straightforward. Now for my next one, 78 Fahrenheit to Kelvin, I'm going to use both formulas. And so I start with my Fahrenheit 78 equals 1.8x plus 32. Subtract 32 from both sides would give me 46 equals 1.8x. Now divide by 1.8 on both sides, and I get 25.6 equals the centigrade temp. Now I'm going to go over and put my 25.6 in for my centigrade, my Kelvin formula, and I just have to add them together, and I get 298.6 Kelvin for my answer. So that's pretty straightforward. And I'm going to just get back to my arrow. Okay, here we go. All right. Next topic, scientific notation. It's used to write very large or very small numbers in a nice compact format. And you can see over here on the side, here's an example of it. You might remember how to do this. Here's an example here. I'm going to go through this in the next slide. Can you read how much these numbers are? So the first one, that's going to be 8 millionths of a meter. And I can tell just by looking at the power of 10. And here's the opposite, a very large number, that's 4,500,000. And that's how we'd write that in scientific notation. Now this is the basic format for scientific notation. You have a number that has to be between 1 and 10. It can't be 10, it can be up to 9.99. It has to be 1 or more but less than 10 times 10 to a power. And this power will either be a positive or negative whole number. It could even be 0, but there's no point in writing that. Okay, so here we go again. So let me go through a couple of them with you. So we start off with 4,500,000, and I'm breaking that down into 4.5 times a million. And now I'm going to work on the million. So a million would be 10 times itself 6 times, which I can then write as 4.5 times 10 to the 6th. Now, a simpler way to do this would just be to move the decimal point. So if I go back to my pen again, here's where my decimal point would be. If I were to move that decimal point down and stop it between the 4 and the 5, that would give me a number between 1 and 10. And then if I count the number of places I moved it 6 places. And that's going to give me the power. Now this was a real big number, and I made it smaller by moving the decimal point in this direction. Therefore my power of 10 would be positive. Now let's look at the other number. So now we have 8 millionths, which can be written as 8 times 1 millionth. And I'm going to work on the 1 millionth. So 1 million can be written as 1 over a million, or it can be written as 1 times 10 to the 6th. Now 1 over 10 to the 6th can be written as 10 to the negative 6th. So this negative sign down here, that just means 1 over. The other way to get it would be to move the decimal point all the way down and stop it just past the 8. And then count the number of places I moved it, which was 6 places. But in this case, I moved it 6 places to make the number bigger, and therefore the power of 10 becomes negative. Let me get rid of my pen now. All right. So here are some for you to try. So you might want to pause the video now, copy these down, answer these, then come back up and check your answer. All right, and here are the answers. Here are the first 3. Remember, moving the decimal point in whatever direction to get a number between 1 and 10. In the middle group, you're asked to convert these back to regular numbers. So this would say move it 3 places to make the number bigger, move it 4 places to make the number smaller, move it 7 places to make the number bigger. And here are our answers. And the last one, which is the greatest and which is the least? That's really, we get that by looking at the power of 10. So the question is, which power of 10 is the greatest? And it's this one. And those are our answers. Okay. Next topic is the meaning of numbers. Well, numbers are used for 2 different things. They're either counting or measuring. And we actually view numbers differently when we do this. Exact number is a number that's derived from definitions or from counting objects. And here are 3 examples. 1 foot to 12 inches and 1 kilometer to 1,000 meters are examples of definitions. 32 students in the room we get from counting objects. So whenever we count objects or use definitions, there's no such thing as accuracy with these numbers. But with measured numbers there is. How accurate a measured number is will depend on the instrument used to do the measuring. So if we have a very accurate instrument, we can get a very accurate measurement. But we can never get an exact measurement, because every single measurement has some uncertainty with it. And this will hopefully show you that. So here we have an example. It's 400 miles from Boston to New York. Believe it or not, they're supposed to represent Boston. So how accurate do you think the 400 is? Does it mean 400 not 401? Or does it mean 400 not 500? Are the zeros actual measurements or just placeholders, meaning they needed to write the numbers? So we have to have rules for this. And now we're getting into the topic that causes problems for many people, and that's called significant figures. Remember, significant figures only refer to measurements. So all the significant figures will be all the certain digits in a measurement plus one uncertain. And here's an example of that. So I have 3 different measuring instruments. They're all meter sticks, but the first meter stick is not graduated at all. The second meter stick is graduated into groups of, looks like 10. That would be 10 centimeters, I mean. And here we have, you can see many more graduations. It would be 100. In fact, this is 100 centimeters here, all these little lines. Now, notice that we kept the distances all in meters. That's really because of the first one. So, first question is, how many significant figures will be in each measurement? Well, for A, it's going to be 1. For B, it's 2. And for C, it's 3. The only number that wasn't a significant figure was a 0 in front of the decimal point. Its whole function is to make you note that there's a decimal point there. Which digit is the estimated one? In the first, it's the 6. In the second, it's the 1, and in C, it's the 7. So all measurements have one estimated digit, and that's the uncertain one. They have to have one. You can't have more than one. So it would have been wrong up in here in A if somebody had said, I think that's 0.65 meters. Because if they're guessing at the 6, they'd know nothing about the 5. Okay, now let's go over the rules for significant figures. And it's really all about the zeros. All right, the first rule, a number is a significant figure if it's not a 0. And here are examples. Notice that's 2 significant figures. 5, that's 5 significant figures. If a 0 is between non-zero digits, like you see here, the 0 is considered to be a measurement as well. So that's 3 significant figures, and that's 4 significant figures. So these are obvious. And if that is not so obvious. A 0 at the end of a decimal. If there's a decimal point in a number, like you see here, those zeros are going to be significant. So here, 50 liters would be 2 significant figures. And what this means is 50, not 51. 25.0, 3 significant figures. This means 25.0, not 25.1. So if you have a decimal point in a number and it has zeros, those zeros will be significant. And here we have 2 numbers in scientific notation. Anytime you have scientific notation written, those numbers to the left of the X are always significant. You don't have to worry about whether they're zeros or not. The power of 10 themselves, never significant. And the last rules. See, at the beginning of a number. So if zeros begin a number, those zeros are not considered to be significant. They just needed to write the number. So the one significant figure here is the number 4. The 7.5, that's 2 significant figures. If you have numbers with no decimal point, those zeros are looked at as just placeholders as well. So 850,000, only 2 significant figures. 1,250,000, only 3 significant figures. You have to know how many significant figures there are in a measurement by just looking at it. That's going to be your goal. So you might want to review these a bit before we try any quizzes on it. Just to review with the zeros, they're not significant if they're only placeholders. And here's the examples where they're not significant. When they end the number, but there's no decimal point. When they begin a number, they're not significant. Zeros are significant if they're actual measurements. And here are the examples. If you have zeros with a decimal point, these zeros are significant, or a zero trapped between non-zero digits. Now here, in this example here, you see decimal point. These zeros are also significant. They have nothing to do with writing the amount. They're not needed for that, so therefore they must be actual measurements. And that first zero, that's never significant. All it's doing is calling your attention to the decimal point. So let's see how you would do here. So you might want to pause this and write on a piece of paper how many significant figures you think are in these measurements. And then we'll come back and check it out. Okay, here are the answers. 3, 3, 3. These are pretty straightforward. A lot of people might not have got D right. D is just 2, E it's 4, and 7 just 1. Now some people would say, well, this is kind of undefined. Is it 1, or do they mean more significant figures? So how can we make a number like this have more significant figures than just the 1? That's what I'm going to show you next. Now here is the number 7,000 written 3 different ways in scientific notation. The first way, that's only one significant figure. The second way it's 2, the third way it's 3. So there are ways to write numbers like that 7,000 with different numbers of significant figures. The key is to put it into scientific notation. Now there are rules for adding and subtracting measurements, and there are rules for multiplying and dividing, and they're different from each other. So we're going to go through them one at a time, and then I'm going to end by giving you some to try. Adding and subtracting. We just look to the right of the decimal point. Let me get my pen here. So what we're going to look for is right here. So I'm going to come and draw a line there. So we look to the right of the decimal point. So you see we have 3 digits over here. We have only 1 here. Because there's only 1 here, I want to round off my answer so it only has 1. And that's why I rounded off to 90.4. I just dropped the 3 and the 2. Now if this 3 had been a 5, I would have added 1 to the 4 when I dropped it. Now here's one for you to try. Maybe you want to stop and write down what you think this number should be rounded off to. Again, if we draw a line through this, like that, you notice we have 2 digits to the right of the decimal point. Here we have 4. Our answer then can only have 2. We get our 0.79. Multiplication and division is a little bit different. We're going to consider the entire measurement. So here we are multiplying these two together, and this is what we get for an answer. So there are 3 significant figures here, and there are 5 significant figures here. So how many should I round my answer off to? Well, the rule is stating that I want to write my answer in such a way that it has the same number of significant figures as the smaller number of significant figures. Therefore, I want 3, and I get this for an answer. Okay, here's one for you to try. 6.8 divided by this gives us that for an answer. How many significant figures should I have in my answer? Well, this is 2, and this is 5. How many should this be? Well, the answer would be 2. So how can I make this 2 significant figures? Well, my first significant figure is the 6. So I only want to keep these 2. But when I drop the rest of them, you notice that that 6 is greater than 5. So I'm going to add 1 to the 0, and I get 0.061 for an answer. All right, now here are 4 for you to try. You want to copy this down on a piece of paper, do the math, and then come back and check. So you might want to pause the video at this point. Okay, and here are the solutions. First of all, I put the rules at the top. Remember that in addition and subtraction, the number of decimal places in the answer is determined by the number having the lowest number of decimal places. In multiplication division, the number of significant figures in the answer is determined by the measurement having the smallest number of significant figures altogether. All right, let's go for A then. So for A, we're adding these two together. Line that right up like that. And you notice that we rounded this off, so it only had 1 digit to the right of the decimal point, and that's because of this guy up here. And here's B. Now we're subtracting, and you notice that this guy has 2 to the right, while this one has 3. So we round off our answers, it only has 2 digits to the right. And because we're dropping that 7, we make the 7 here become an 8. And this is the next one. Here we're multiplying, so we have 3 significant figures here. We have 5 here, so our answer must be rounded off to 3. Now we count the entire number when we're multiplying, not just to the right of the decimal point. And that's why we get that answer. And then the last one we're dividing, and both numbers have 3 significant figures. And so when we divide, you notice that the units don't go anyplace because they're different. They won't cancel out. We get this for an answer. So we want 3 significant figures in our answer. You have to remember that these zeros are not significant. So our 3 significant figures are going to be these 3. Again, because we're dropping that 4, it won't affect the other 4. And that's how we get this for an answer. Now any number like that, that's that small, should be written in scientific notation. And so we'd move that decimal point down, stop it just past the 1. We get this, and we notice we've moved it 4 places, so we get -4 for an answer.